Alright, so here's what we're trying to do. We launched a, let's see here, projectile from the top floor at Student Services and had it land down on the floor in the Media Center. So we were doing math on this projectile to see if we could predict, using reasonable mathematic approach, where on the floor will this land. So in other words, what is the horizontal range? And the horizontal range of this object would be found by figuring out what the horizontal and vertical components of the velocity are. Well, we know the velocity coming out of the projectile launcher is 5.4 meters per second. And let's just say that we're going to use an angle here of something simple like 30 degrees. And so we want to figure out then what is the horizontal and vertical components of this. So the horizontal component is coming out of this thing at like so. Well, I'll just draw it down here even though it's not. So the horizontal is there, and then the vertical component is like this. Okay. And out of all this information, one of the things is the horizontal velocity stays constant, so it's steady, steady, steady the whole time. And the vertical is going to change. So it starts out at this and it gets less and less and less as this makes a trajectory path, and then it at some point turns around. So the velocity starts out here, it gets smaller and smaller until it gets to a certain height. At that height, at max height, then the vertical velocity goes to 0, and then it starts heading back down, and so it's accelerating all the time at negative 9.8 meters per second squared. So it's the vertical component that's going to tell us the time it's in the air. So the v vertical initial is going to be 5.4 times sine of 30 degrees. And the reason we're using the sine is because relative to this angle, this is the opposite side. So opposite side uses the sine times the hypotenuse. So 5.4 times sine 30, and I'm just nerdy enough to know that sine 30 is 1/2. So half of 5.4 is 2.7 meters per second. Okay, so the initial vertical velocity, v initial vertical, is 2.7 meters per second. Well, v initial horizontal we'll get to in a minute because we're going to need that for the range, but v initial vertical will help us figure out the time. So the height that this thing is, oh no, there we go. The height that we figured out from the Student Services railing is 5 meters. I think it's actually 4.8 or something to that effect, 4.9, but we can round it to one significant figure and call it 5 meters. So height final, the formula that we're going to use to calculate our time, height final is equal to 1/2 gt squared plus v initial vertical t plus height initial. So this is in the quadratic form, being height final is 0. Half of g is negative 4.9 t squared, plus vertical v initial is 2.7 t plus height initial, which is 5 meters. So now we have our quadratic form in the situation where you can plug it into the formula and get it to spit out an answer. So A, as always, for a projectile is negative 4.9, because it's always going to be 1/2 g. B is always the initial v, or v initial vertical, so 2.7. And C is always the original height, which is 5 meters in this case. So you plug that in and you'll get your time Once you get the time of flight, then you take it and multiply it by this horizontal velocity. So the horizontal component of the velocity is 5.4 times cosine 30, because this is the adjacent side relative to that angle. So the adjacent side is equal to hypotenuse times cosine of 30, and you're going to get a number for that. You take that v horizontal velocity and you multiply it by this time that you plugged into your calculator, and you get the range, which is equal to v horizontal times time, because that comes from velocity. Oh wait, hold on a second. Velocity equals distance, which is the range, divided by time. So velocity times time, multiplying both sides by t. Those cancel. V times t is the distance, which is the range. All right.